Welcome to the second lecture of the module on astrophysics of neutron stars. In this lecture, we would discuss some phenomenology of the radio pulsars. Now, radio pulsars, as we have seen in the last lecture, send very periodic pulses of radiation. Those periodic pulses vary widely from pulsar to pulsar. As you can see in these different profile shapes, that these shapes of pulses differ significantly from pulsar to pulsar. Not only that, the shapes also change with different energies within the radio band. Then again, if we go to higher energies, then the pulse shape changes rather significantly from radio to other energy bands. For example, here are some profiles of various known pulsars in different energy bands. The top one is radio, then the second one is optical, then X-ray and then gamma ray, and there are some very well known pulsars, namely Crab, Vela, Geminga, and you will see that the pulse shapes change significantly from radio to optical to X-ray and to gamma ray. So, now let us understand the nature of this emission. For example, for any object emitting radiation, we can naively assume that object to have a black body radiation. In that case, we would equate the intensity of radiation that is being received from that object to the black body intensity of radiation at that temperature. So, in other words, we would equate this I omega, which is our observed intensity, to the Planck function, which is given by this well known formula, and we would try to see what would be the temperature of this emitting region. Now, if the photon energies are much smaller than the corresponding black body temperature, in that case the Rayleigh-Jeans approximation of the black body would hold. It is a well known formula, and using this Rayleigh-Jeans law, we would be able to directly estimate the temperature of such an emitting region. Now, if we apply this formula for the pulsar emission, a typical intensity obtained from a pulsar in the radio band is about 10 to the power 4 to 10 to the power 7 ergs per second per centimeter square per hertz per steradian. Now, if we use the Rayleigh-Jeans law for this amount of specific intensity in the radio band, what we obtain is a whopping 10 to the power 23 to 10 to the power 26 Kelvin as the black body temperature. Now, clearly this is ridiculous, this is an absurdly high black body temperature, and it would be almost impossible to accelerate particles to such energies, and also the radiation would be in a much higher frequency compared to the radio band in which you are actually seeing this radiation. So, very clearly the pulsar emission is not black body radiation. As we have seen in the previous module, the radiation actually comes because of the presence of extremely strong magnetic field, and this has been explained in the previous module how this radiation comes about. There is a neutron star which is rotating at a very fast rate and has a strong magnetic field. because the magnetic field is time varying, a very strong electric field is generated in the region immediately outside the neutron star, and that region is called the magnetosphere. Now, there is a radius we can define, a distance from the center of the neutron star, which you call the light cylinder. If you estimate the velocity at this radius, which is in sync with the spin period of the neutron star, then the radial velocity becomes equal to the speed of light at such a radius. Clearly, magnetic fields extended up to this light cylinder can co-rotate with the neutron star, but magnetic fields which would go beyond this light cylinder radius would not be able to co-rotate, and they are called the open field lines along which particle can stream around. Now, in this region of closed field lines that close within the light cylinder radius, there would be huge amount of charged particles. The particles which will basically neutralize the electric field, and this region is known as the space charge limited region. Now, the emission that is coming from charged particles being accelerated along this open field lines, this is the radiation that would be received by any observer outside, and this radiation is basically generated by curvature radiation, synchrotron radiation, Compton scattering and such plasma process radiation. Now, in this region, what is interesting is the region is totally dominated by the magnetic field. If we, for example, calculate the force on an electron due to the presence of the electromagnetic field there and gravitation, then we have this quantity which is F gravitation by F electromagnetic, and for a magnetic field of 10 to the power 12 Gauss, which is typical for an ordinary radio pulsar, and a spin period of 1 second, this ratio becomes 10 to the power minus 12, which means that gravitational force on a charged particle in the neutron star magnetosphere is basically negligible. So, the charged particles are basically being driven by the electromagnetic considerations there. This magnetosphere within this region is force free. It follows an equation given by E plus 1 over c omega cross v equal to 0, that is the Lorentz force is 0 there, and therefore, this imposes a condition on the charge density of the particles there. The charge density comes from the Maxwell relation, and we obtain this. The charge density is given by the rotational frequency and the magnetic field of this form, and here E is the induced electric field in the magnetosphere. Now, we have so far been considering a dipolar magnetic field. Now, let us consider the geometry of such a field. Consider this to be the center of the neutron star, and this is the rotational axis, and that is the dipolar magnetic field. So, that is the m is the magnetic moment vector, and the angle between these two axes is alpha. This is called the inclination angle of the magnetic field. Now, given that, we could write the magnetic moment by this formula, m equal to half b p r cube multiplied by cos alpha, and unit vector parallel to the rotation axis sin alpha cos omega t, omega is the spin frequency of the neutron star, cos omega t E perpendicular, sin alpha sin omega t E prime perpendicular, where E perpendicular and E prime perpendicular are two unit vectors perpendicular to the rotation axis. To note here, B p is the surface dipolar magnetic field and r is the stellar radius. So, this is the model that we are using to estimate the radiation from a neutron star. Now, the neutron star is emitting a radiation. We are assuming a rotating dipole model, and the time variability of this rotating dipole is giving us radiation. Now, this radiative energy is coming at the cost of some other energy, and basically what we see here is that the radiation comes at the cost of the rotational energy. Now, the radiative energy for a pure dipole configuration is proportional to the square of the double derivative of the magnetic moment, which becomes proportional to B square. Again, B is the surface polar field, and omega to the power 4, where omega is the rotation frequency. Now, the rotational energy, derivative of rotational energy is given by I omega omega dot, where I is the moment of inertia of the neutron star. Now, equating these two, assuming that the radiative energy comes exactly at the cost of the rotational energy, we obtain an estimate for the dipole field, and this is given by some proportionality constant multiplied by spin period multiplied by spin period derivative to the power half. So, magnetic field is proportional to the square root of P p dot. Now, this is something which is useful to remember. Now, there is a radiative slowdown because energy is going away. So, E dot rotational is less than 0, omega dot is less than 0, and from this we can define a characteristic age of the pulsar, which is given by P by 2 P dot. Now, this is valid if we assume that P 0 s, that is the initial spin period, the spin period with which the neutron star was born, is much smaller than the spin period that we are seeing today. Now, the slowdown could be because of other processes as well. For example, there could be gravitational radiation too at the cost of rotational energy. The same physics follows. E dot gravitational wave less than 0, which implies omega dot less than 0. Now, the existence of a rotating mass quadrupole moment gives rise to gravitational radiation, and if we calculate the E dot gravitational wave for that radiation, what we obtain is a omega to the power 6 dependence with the E dot. So, now we have I omega omega dot proportional to omega to the power 6. This I here is the moment of inertia and others are fundamental physical quantities, except this epsilon here, which is the ellipticity from where a mass quadrupole moment is being generated. Now, we can again define a characteristic age for this gravitational radiation. Typically, such an age, the gravitational wave radiation would be much larger than the characteristic age estimated by the electromagnetic radiation. The actual slowdown is a combination of the electromagnetic and the gravitational wave radiation. So, let us discuss another important concept in the radio pulsar phenomenology, which is the timing of radio pulses. Now, for this let us define something called time of arrival. As you see, here is a neutron star which is rotating and the magnetic field axis is directed towards us, towards our telescope, and we receive the radiation beam from there, and it is received in an electronic receiver, and the signal is dispersed and it is folded in the sense there are many pulses coming from the star which are folded together to obtain a sensible signal to noise ratio, and then we have a mean pulse profile. Now, how do we define a time of arrival for such a pulse profile? We do the following. It refers to a particular fiducial point on the profile. As you can see, this profile is a wide thing, and we specify a particular point, maybe at the maximum or at some other point, and we calculate the delay with respect to a template profile. So, what is a template profile? A template profile is obtained by prior observation of the same pulsar. So, we observe the same pulsar for a long period and we average the pulse profile, and from there we obtain a template profile. So, this average profile of a pulsar which is extremely stable over very long time scales is used as a template profile. Now, we use that template profile, and then after we have obtained a particular pulse, for example, and we have specified a fiducial point, then for the next pulse we know when it should arrive. Now, any delay with respect to the template profile is called a delay in the time of arrival. So, the profile that we obtain, for example, today would be given by this P t, where this is our observed profile, and this is expanded in terms of A, which is shift, and B multiplied by the template profile plus some noise. Now, this template profile is given by T minus tau, where tau is the time shift between the observed profile and the expected arrival time. Now, how precise is the TOA calculation or the TOA that we obtain? Certain quantities are defined to understand the precision with which we are doing the timing of a particular pulsar. The uncertainty of our precision is defined by a quantity sigma TOA, which basically depends on a number of quantities in our observational system. So, for example, the system equivalent flux density, then the signal to noise ratio, then the integration time, how long we are observing, and delta f, the available bandwidth. So, these are all observational parameters of our experiment. On the other hand, it crucially depends on the intrinsic pulsar parameters, what we are getting from the sky. So, the mean pulsar flux density, the pulse period, the width of the pulse and also the duty cycle of the pulse. By duty cycle one means the time for which the pulse is observed within one spin period. There is also another quantity called the quality factor, which is defined by this formula, where S peak is the peak pulsar density. Higher value of Q implies we are doing a better timing of the pulsar. And why we are interested in these quantities is what we have discussed in the previous lecture, is that pulsar timing is very important for various experiments that we undertake. The precise timing gives us a very good clock, an astronomical clock. We can do gravitational wave detection through pulsar timing arrays, etc., etc. Now, we have seen that there would be delays in the time of arrival, but what are the reasons for such a delay? Now, we can actually pinpoint the reasons for such delays. For an isolated pulsar, the time delay in the solar system barycentric coordinates, that is called TSSB, is a sum of a number of quantities. The topocentric delay, the delay measured at the observatory at the local coordinates, that is what we measure, plus T corrections, various clock corrections that we have to incorporate. Then this term refers to the correction for dispersion measure, because we are not observing at a precise frequency, but over a wide frequency band. So, dispersion measures need to be incorporated in our calculation. Then the Romer delay, which is basically light travel time from the telescope to the barycentric, the solar system barycenter. Then we have Shapiro delay, which is basically the correction factor due to the curvature of space time on the path of the radiation, and Einstein delay, which is the delay caused due to gravitational redshift because of the presence of massive objects, and also the time dilation because of the movement of the earth. Now, here is an example where various factors have contributed to the timing solution. See, for example, see panel 1, this is totally random, and so there are no unmodeled effects. We have been able to extract all the possible causes for the systematic delay. On the other hand, this panel B shows an error in the frequency derivative. So, you have not estimated P dot correctly. Panel C gives error in the position, we have not estimated the pulsar position accurately, and panel D gives unmodeled pulsar proper motion, we have not corrected for the proper motion, the velocity of pulsar in the sky. Now, for a binary pulsar, life becomes much more complicated, because the two stars, the neutron star and its companion, are rotating around each other, and there are several important effects that we have to consider. Now, this particular figure refers to a double neutron star binary. Both the components of the binary are neutron stars, and such binary systems are very important to us, because careful timing of such binary pulsars allow us to measure various Keplerian parameters like orbital period, semi major axis, eccentricity, epoch of periastron and epoch of the ascending node. So, all these parameters allow us to very precisely determine the mass of the neutron stars, as we have discussed in passing in the previous lecture. So, that is why accurate timing of binary pulsars are very important. Now, for binary pulsars, there are additional factors over and above the factors we discussed for an isolated pulsar causing time delay. What are those? Those are additional Romer delay due to binary orbit, additional Shapiro delay due to the binary orbit and additional Einstein delay due to the binary orbit, and also a factor of aberration caused by the orbital motion. So, there are whole lot of factors one needs to take into account in order to have a precise timing of pulsars. Finally, let us discuss about an interesting phenomenology that is observed for radio pulsars, that is the phenomenon of nulling. Now, for an ordinary radio pulsars, you would see the pulse trains would appear regularly. So, you would have a very regular train of emission pulses. For a nulling pulsar, what would happen is there is a regular train of pulses and suddenly a few of them would not be there. So, suddenly the emission would disappear. So, basically we have an abrupt cessation of emission pulses that disappear. Now, an extreme case of nulling pulsars are called the extreme nullers, where they only appear every now and then in regular pulses. Most of the time we do not see them at all. And even more extreme case, one really does not know whether these objects are connected to the top two, are called RRATs, rotating radio transients, which are seen in sporadic single pulses. So, this behavior is again very varied. You will see different kind of nulling patterns coming from different pulsars. Here is a patchwork made of the nulling patterns from 6 different pulsars. These black points are the pulses which have been observed. You will see that for this pulsars, the gaps, that is the nulling phases, are more or less regular, they appear regularly. For this object, even though they appear regularly, they tend to be much longer than this pulsar. So, this one has much longer nulls. In comparison, this third one has very small nulling phases interspersed by long active phases. This one is mostly absent and seen only here, and similarly there are wide variation in the nulling patterns. They are also associated with this nulling behavior with other peculiarities of radio pulsars. One is drifting of subpulses. In this diagram, simulated and observed behavior of this pulsar B0943 plus 10 is being shown. So, this is a simulated drifting of pulses and this is a real observation. So, what is happening is this is the longitude axis and you would see that the pulses seem to drift within a pulse period. So, they go shifting and shifting and shifting. So, this drifting of subpulses typically appear to be associated with nulling. Now, the same pulsar that we saw in drifting of subpulses, it is of course a nulling pulsar, also experience something called mode changing. What is mode changing? You will see in this picture. It is emitting in radio and then suddenly the radioluminosity drops and simultaneously X-ray luminosity increases and vice versa. So, here in this top picture, this is when the radio luminosity is high, you see radio profile very strong and X-ray profile very weak, and in the different mode the X-ray is strong, X-ray profile is strong and the radio profile has become weak. So, this is also a phenomenon which is associated with nulling. Now, the nulling behavior, which is abrupt cessation of pulsed emission, is associated with drifting of subpulses, associated with mode changes, also associated with switching emission frequencies. We have seen that more energy is emitted in a different frequency when the mode changes, and there is also association with change in the period derivative. So, the period derivative changes because at the time of nulling there is no emission. So, therefore, charged particles are not taking away energy from the pulsar. So, that component of energy being lost by the pulsar becomes smaller and therefore, the period derivative, which is a measure of the loss of rotational energy, also changes. But this is not seen in all nulling pulsars, but only a few nulling pulsars. So, this particular explanation may not hold good because it is not seen everywhere. Now, the characteristic of the nulling population is like this. There are about 200 nulling pulsars. Let me remind you, there are about 2500 radio pulsars that have been seen, and only in 200 we have observed nulling, but that is not an indication of the fact that this is the fraction of pulsars which undergo nulling, because most of the radio pulsars are not observed continuously, they are not monitored. So, if today some of the pulsars are nulling and we are not looking at them, then we would not know. So, we only know about 200 pulsars which are nulling, there may be many more. The period of the nulling pulsars are reasonably high, they are slower kind of pulsars. The spin period ranges from about half a second to about 10 seconds, and correspondingly the magnetic field is on the higher side between 10 to the power 11 Gauss to 10 to the power 13 Gauss. There are also somewhat older pulsars, the age being 10 to the power 6 to 10 to the power 8 years, and they are not concentrated in any particular region of galaxy. The DM dispersion measure, which is an indicator of distance, has a quite large range. So, therefore, pulsars all over the galaxy show null. Now, in order to characterize these pulsars, we have defined two quantities. One is the nulling fraction, the percentage of time that a pulsar goes nulling, and it has been seen that from a percentage of very few to almost 95%, there is a huge range in this nulling fraction. And the other quantity that has been defined is the nulling length, the time for which a pulsar remains in a nulling phase, though there is not much data on the nulling length. However, neither nulling fraction or the nulling length is an unique marker of a particular nulling pulsar. Why? Because an individual nulling pulsar can be seen to have different nulling fractions in different phases and similarly different nulling length in different phases. So, these are not unique markers. Nevertheless, depending on the length of the nulling phase, some classification has been made on these nulling pulsars. So, there are classical nullers, only a few pulses are absent and most of the time the pulsar is seen in emission. Then there are intermediate nullers, the nulling phase, the null length can be as long as a few hours. Then intermediate pulsars, which are nulling most of the time, even for as long as several years, and then they come up in emission. So, these are called intermediate pulsars, and we have already talked about RRADs, which are characterized by sporadic single pulse emission. Now, nulling fraction is the only quantity for which we have sufficient data, and it is seen that this quantity does not have any obvious correlation with any of the measured intrinsic pulsar parameters. For example, here nulling fraction has been plotted against pulsar period, magnetic field, dispersion measure and characteristic age. As can be seen, there is no obvious correlation with any of these quantities, except for the fact that, note this gray band, there seems to be a sort of break in that band around 40%, but as I have said, the observation on nulling pulsars is small, and maybe with better observation this tiny band would disappear, and there may not be any intrinsic physics associated with this band. Now, something that we understand about the nulling pulsars is this. Originally, there has been a suggestion that because some of the emissions are disappearing, perhaps the radio pulsars are about to die, in the sense they are about to cease their emission. Now, there is something called a death line, which is defined for radio pulsars. It is a line in the spin period magnetic field plane. It is a combination of the spin period and the magnetic field, beyond which the radio pulsar emission mechanism, which is dependent on the strong field and fast rotation, the mechanism would not function, and therefore, a neutron star, even though it might be rotating, even though it might have a magnetic field or what have you, it would not be visible as a radio pulsar, and such a line is called a death line, which are shown by these straight lines in this plot. Now, these different lines assume different kind of magnetic fields. As we have said that the magnetic field is dipolar, but that may not be correct, and we will talk about that in the next lecture. So, different kind of magnetic field configurations can be present in different neutron stars. So, assuming different kinds of magnetic fields, different death lines have been proposed, and what we see, all these red circles here are radio pulsars that are nulling, and all the gray dots are radio pulsars for which we do not have any information whether they are nulling or not. And you will see that most of the nulling pulsar are constrained by one of the death lines, and these blue stars are actually the intermediate nulling pulsars. Now, this death line by which the nulling pulsars are being more or less constrained is a death line which has been generated by assuming extremely carved magnetic field. So, is it possible that the nulling pulsars or the pulsars which are experience nulling have extremely carved magnetic fields? We do not know yet, future observations might tell us about it.